Okay, so number 8 in your book. So here we're still applying the theorem, but it says apply the translation theorem to find the inverse Laplace transforms, right, of the following functions from 5 through 10. So we're given number 8. And again, if you turn to page 290 and you look at the table, the first column, right, we have our f of t's, and the second column you have your capital F of s's. And we want it in that form, right? Some numerator over a denominator, right, with a translation of maybe s minus a quantity squared or cubed, maybe plus another square. And so here, the main thing you need to remember from algebra is how to complete the square, because we're going to complete the square on this polynomial, all right, a polynomial in S. So let's go ahead and do that first, because that's going to help us, it's going to help us transform, no pun intended here with the actual Laplace transform, it's going to transform this guy, and it's going to hopefully change it to maybe something, a quantity, right, some translation squared to another square. So let's go ahead and do that. So we're going to complete the square, right? So this is from your algebra days. Okay. So I'm going to have my polynomial s squared plus 4s plus 5. Okay, so this should remind you, again, if you want to fast forward this for the completing the square, if you remember it, that's great. But again, I want to make sure we're on the same page. This should remind you of ax squared plus bx plus c, right? I just have an s here for x. And again, we can complete the square here, and when we complete the square, let me go ahead and rewrite this, s squared plus 4s plus 5. We only focus on the first two terms. That's where we want to complete the square. And remember, we want to, I'm going to again rewrite s squared plus 4s. I want to add a square to this these two terms, because I want to create a perfect square trinomial, because perfect square trinomials factor very nicely. And then of course I have my, let's maybe put brackets here. I still have my 5 here. Now whatever I add here, I'll just put question mark, I'm going to subtract here, right? Because I'm really, I mean, if I'm adding 5 and I subtract 5, well, I'm not really changing the value of this expression, because I'm really adding 0, and we can always do that. Okay, so let's complete the square. So I have s squared plus 4s plus, and then how do I obtain, right, this guy? Well, all you have to do is, we're looking at this guy, and you take half of it and you square it. So half of 4 is 2, and if we square it, it's 4. So we take, right, half of our b, if you want to call that, in our polynomial. So I'm really adding 4. So if I'm adding 4, let me just put that in brackets, I'm really subtracting 4 here. So plus 5 minus 4. Okay, so that's completing the square. Now this guy, right, this is a perfect square trinomial, meaning the factors are exactly the same. So if you factor this, right, this is s plus 2 quantity squared, right? S plus 2, right, if you FOIL this, you will get, you know, this polynomial above, right? It's not s squared plus 4. We need that 4s. Plus, right, and this guy is just 1. Okay, so this is what I want. So remember, the numerator was s plus 2, so let me just go ahead and rewrite it. So we have f of s equals s plus 2 divided by s plus 2 squared plus 1. So now let's take the Laplace inverse of s plus 2 divided by s plus 2 squared plus 1. And remember, right, you cannot divide these out, or one factor of it, because we're adding. So please don't do that. It's a common error, but make sure not to do that. So what's, you know, this guy equal to? Well, now we look at our table, our second column, are f of s's, and this is looking like right? This expression here looks very similar to s minus a over s minus a squared plus k squared, which is the cosine, e to the at cosine of kt, right? Where this is my f of t, right? And of course, this guy is my f of s. So we know it's going to be cosine t. So the Laplace inverse, right? Okay, so let's just write this guy again. Doesn't hurt to practice writing it. Okay, so s minus a, what's my a? Well, remember this guy, this is just really minus 2. So our a is really negative 2, but we can just rewrite it as s plus 2. It means the same thing. But our a is negative 2, and let me go ahead and erase that because I want my f of t, and oh, of course it's not letting me erase. Okay, so let's ignore that guy. So e to the at, right, I'm looking at this guy, e to the a t times cosine kt, and my kt in this case, my kt, right, my k is 1, right, because it's 1 squared, k squared, and it's cosine because it's s minus a, right? I have a term s up here. It would be sine if it was just some a. So cosine kt, so cosine t, so that's it. That is the Laplace inverse of this function is equal to this specific f of t. Again, the strategy here is remembering to complete the square.